Welcome back to Honors Calculus. In this video, we're looking at differentiable functions. A derivative and a differentiation is the process we talked about in the previous video of finding the equation of a tangent line, or specifically finding the slope of a tangent line. So let's start with that. If we have any function f, we can define the derivative of f as a new function, f with an apostrophe after it, which we read as f prime. And f prime is the function mapping from R to R, defined by the limit of the quotient that we looked at last time. F prime of c is exactly the slope of the tangent line when x is equal to c. That's the definition that we used here. So as an example, let's consider the function f of x equals x squared that we've been dealing with. And we want to find an expression for the derivative f prime of x. And there are other tools that we could use, but for right now, the only tool we have at our disposal is the limit definition. So f prime of x is the limit as delta x goes to 0 of f of x plus delta x, and we're looking at the squaring function, so that's x plus delta x, the whole thing squared, minus f of x, that's x squared, all over delta x. You can check that if you plug in delta x equals 0, you will get 0 over 0 indeterminate form, so we know we have work to do. The work is going to look very similar to what we've seen previously. Multiply out that power on the group, we'll have x squared plus 2x delta x plus delta x squared minus x squared all over delta x. The x squareds will cancel out, leaving 2x delta x plus delta x squared all over delta x. And we can divide off the delta x's and get 2x plus delta x. And as delta x goes to 0, that just becomes 2x. I invite you to go back to the problems that we've solved previously, where we looked at specific values, and try plugging in those x coordinates, x equals 1 and x equals 3, if I remember correctly. F prime of 1 is 2, f prime of 3 is 6. Those numbers should be pretty familiar to you based on what we were doing in the previous video. All right, so that's all fun and good. That's something that we certainly can do. But continuing onward, we'll say that a function f is differentiable at a point C if the derivative f prime of C is defined. And just like we had with continuous, we can extend this idea out. F is differentiable on AB if and only if f is differentiable for every C in AB. We don't have a way of defining differentiable on a closed interval. I guess I should say we technically do, but it is really messy, not useful, and will be on the scope of this course. And then finally, f is differentiable everywhere if it is differentiable on the interval from negative infinity to positive infinity. All right, very similar definitions to what we've seen in the past. With the idea of continuous. And so as an example, we can try to determine the largest interval containing x equals 0, where the function f of x equals 1 over x is differentiable. And this is one that, just like with continuous, we can talk about, well, the largest interval, if it's unbounded above and it's unbounded below, there's no measure of which one is larger, at least in what we've talked about this far in our discussion of mathematics. So we have to specify. We'll specify the largest one that contains 0, which might be bounded, might be unbounded. We'll find out. But we know that f prime of x is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x and that's the limit as delta x goes to 0 of 1 over x plus delta x plus 1 minus 1 over x plus 1 all over delta x. All right. The algebra here is going to be quite a bit messier than what we've done before, but it should still work out. There's a couple of different ways you could approach this. I think that the most straightforward is going to be to divide this up and then find common denominators, by which I mean that this compound fraction is the same thing as 1 over delta x times 1 over x plus delta x plus 1 minus 1 over delta x times 1 over x plus 1. And multiplying that through, we have 1 over x delta x plus delta x squared plus delta x minus 1 over x delta x plus delta x. All right. And fun side note here, this gives us an excuse to look at a different indeterminate form, because if you plug in delta x equals 0 at this point, you will get 1 over 0 minus 1 over 0, which would be an infinity minus infinity, which can do some really weird things. So that's another indeterminate form. It doesn't show up all that much, but it is something that we should know about so that we can try to work with it. In order to try to work with it, the common tactic is we currently have two fractions. Let's try to write it all as a single fraction by finding some common denominators. All right, so we'll multiply the first fraction top and bottom by x delta x plus delta x. And we'll multiply the second fraction top and bottom by x delta x plus delta x squared plus delta x. And it's really easy to make stupid mistakes here because there is so much going on. But you should end up with x delta x plus delta x minus x delta x plus delta x squared plus delta x all over x delta x plus delta x squared plus delta x times x delta x plus delta x. All right. A bunch of stuff cancels out in the numerator. That's very convenient. And in the denominator, I'm actually going to factor back to what we had before. We got each of these two expressions by multiplying delta x times some stuff. And I'm going to factor the delta x back out, which is convenient because in the numerator, we've got the x delta x is canceling out, we've got the delta x is canceling out, and the only thing that's left is a delta x squared. So we've got minus delta x squared in the numerator in the denominator, we have delta x times x plus delta x plus 1 times delta x times x plus 1. And then these two factors of delta x cancel out those two factors of delta x. And we are left with -1 over x plus delta x plus 1 times x plus 1. And as delta x goes to 0, this becomes -1 over x plus 1 times x plus 1, or -1 over x plus 1, the whole thing squared. Okay, that was a lot of messy algebra, but we got somewhere with it. We just have to remember what we were trying to do. Because remember, the question was find the largest interval and choose the one containing x equals 0 so that this function is differentiable on that interval. And a function is differentiable if and only if the derivative that we found here is defined. So when is this function defined and when is it not defined? It's a rational function, which means it's defined everywhere except when it causes a divide by 0. So it's defined when x plus 1 is not 0, which means that x itself is not -1. So if we wanted the entire interval on which this is defined, it would be the interval from -infinity to -1 union with the interval from -1 to +infinity. But even though it looks like two intervals, this is not an interval, and we were asked to find an interval on which our function is differentiable, and we choose the one that contains 0, and this is the one that contains 0. So the interval from -1 to infinity is the thing that we are looking for. Just a little bit more vocabulary before we wrap up for the day. An operator is a rule that assigns each function to exactly one new function. Put in other words, an operator does to functions what a function does to real numbers. If you continue your study of mathematics, you might eventually get into a course called functional analysis. And in that course, we establish the set of continuous real valued functions, and we start treating operators as functions, mapping from the set of continuous real valued functions to the set of continuous real valued functions, and find that this analogy is a lot more powerful than it seems to be at first glance. But for right now, just knowing that this is a thing that we can do is good enough. And there's exactly one operator that I really care to look at, although I guess I should technically mention that function composition and linear combinations of functions can be thought of as operators in their own rights. They're not all that useful as operators, or it's not all that useful to think of them as operators, but they are operators. because the operators that we care about, the ones that we care to label, are the linear operators. A linear operator is any operator L for which, if we act that operator on a linear combination, a times f of x plus b times g of x, we get a times that operator acting on f of x plus b times that operator acting on g of x. All this video, we've been talking about the derivative, so I guess it makes sense that we'll end with the differentiation operator, which is generally written as d over dx. It looks like a fraction. It's not a fraction. A physicist will pretend that it's a fraction and do all sorts of fraction things with it, and they'll all work. And there's no reason they should, but a physicist can get away with it by saying, well, we only care about places where this works, and yay, happiness. But it's not a fraction, even though it looks like a fraction. Try telling a physicist that, they won't believe you. But the differentiation operator d over dx acting on any function f of x spits out the derivative f prime of x. And I bring all this up because this is the framework that I need in order to show you that the derivative is a linear operator. If you want to take the derivative of a linear combination, a times f of x plus b times g of x, well, you're going to be looking at the limit as delta x goes to 0. I forgot to write down that this is a proof. Let's write that down. Limit as delta x goes to 0 of a times f of x plus delta x plus b times g of x plus delta x minus a f of x plus b g of x all over delta x, which is the limit as delta x goes to 0. Just regrouping some stuff here. This is a times f of x plus delta x minus f of x, grouping together the stuff that has a's and factoring out the a, plus b times g of x plus delta x minus g of x, just grouping together the stuff that has b and factoring out the b, all over delta x. And then the limit itself is linear. That's something that we've proven. So we can rewrite this as a times the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x plus b times the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. And by definition, that's a times f prime plus b times g prime. That is definitely a property that we will be building on in the future, but for right now, it's just an interesting thing we can say about the differentiation operator. All right. I'm going to end with something for you to try. We've seen several times that absolute value is a place where things get really annoying. I'll give you the hint that you are going to have to go back to the piecewise definition of absolute value, and it will work out. But I want you to find the derivative. Uh, Evaluate the differentiation operator on absolute value of x. Find the derivative of absolute value of x, differentiate the function f of x equals absolute value of x. The instructions here can be read in any of those ways, and they all mean the same thing. That's an interesting idea. And then determine the values where the absolute value of x is not defined, where it's not differentiable. Determine what that's going to look like. See what you can do with that, and I'll see you in the next video.